Hello. Do you hear me? Parfait.
Ils seront prêts dans une minute ou deux. Okay, I have to leave within 1 hour. So thank you for coming. I'm very nice to have you there. Thank you. Tu peux essayer de parler?
Hello. Do you hear me? Hello.
Hello. Yeah, we hear you.
Hello. I don't see. I don't know. Hein.
Il est là, ton micro?
Hello. Do you hear me?
Yes, we hear you. Do you hear us?
Hello. Yes, I guess you hear me, but we don't hear you.
Oui, il t'entend, arrête de... C'est bizarre parce qu'on les entend pas, nous.
Non, il faut mais il faut Guillaume. Yes.
All right, we're going to get started soon here. If you could find your seats.
Ça passe par son ordinateur, pas par...
Ouais. Ouais.
Ok.
Ah, il faut que je reprends. Il faut Guillaume.
Guillaume, ça passe pas par les... ça passe pas par les systèmes de...
No, I guess that you have to change in the Amit, in the platform.
All right, if everyone can settle down, let's get started.
Don't worry, not for
so many good conversations. I know. All right.
Just wait before we just have some speaker online.
I hope everyone had a great lunch. Glad you all made it back. We're going to have one more 90-minute session, okay? And then after that 90-minute session, we're going to have a poster session. And we're just going to be able to have conversations until we all get tired. Okay, so there's going to be two 20-minute talks at the beginning of this session. And then there's going to be a sequence of 5-minute lightning talks. And then after that, we're just going to go right into the break and then to posters. Okay?
Okay, just wait a minute. Before starting, we should just solve the problem for Marie and Gordon, who will be speakers. So I just want them to be online, to be put on the stage.
Sorry, I couldn't quite hear you, but if you... Technical problems. Of course, yeah, makes sense. Okay.
Okay, so there are online people that should be put on stage for their short talk, like Gordon, Marie, and Tim. So I prefer that we solve that before starting.
Yep, that makes sense. Okay, so they're there, but they're not showing up. Perfect. Okay, so we're ready to go. Excellent. Okay. All right.
May I go?
I think we are ready to go. So with that, I'm going to introduce Michel, who's in France. He's going to tell us about the variable elimination algorithm as a let term rewriting. So take it away.
Okay, thank you very much. So this is a joint work with Thomas Erard and Claudia Fajan here in Paris. And it is about interconnecting two different domains. On one side, Bayesian inference on graphical models, and on the other side, lambda calculus and term rewriting. So let me just give a short recap of the variable elimination algorithm, which is one of the most basic algorithms for inference in Bayesian graphical models. So we have a Bayesian network that can be represented as a directed graph, as in these examples. The nodes of the graph represent random variables. So in this talk, the variables will be all Booleans, meaning that the possible sampled values will be 2, either true or false. But of course, we can trivially generalize to any finite or countable random variable. And the edges of the graph describe conditional dependencies. So a Bayesian network gives access to stochastic matrices describing these dependencies. So for example, here I write with P of D, a stochastic matrices describing the dependencies of the variable D from the variable B and C. So here we are saying that if the sprinkler is on and it is raining, it is a high probability that my grass will be wet and low probability that it will be not. Now, the question solved by the variable elimination algorithm is fix a subset of variables or a subset of nodes of the graph, and we wanted to compute the joint distribution of the variables associated to these nodes. So, for example, if you wanted to describe the joint distribution of D and E, a trivial way of doing that, a naive way of doing that, is to multiply all stochastic matrices associated to the different nodes of the graph, and then to sum out the variable that we are not interested in. So here we have this multiplication, and here we are summing out A, B, C, that are the three variables we are not interested in. And this gives a vector giving the joint distribution of D of A. So that's simple, nice, but it's a bit inefficient because you can check that it requires about 2 to the power of 5 basic operations. So it is essentially exponential in the number of the nodes of the graph. So it's quite unfeasible for real world models. And variable elimination, improve it by factorizing this algebraic expression by taking profit of the conditional the dependencies and the independencies of the variables as they are modeled by the graph structure. So, for example, so formally the algorithm is written here. It takes as an input a Bayesian network, a list of variables that we want to eliminate. So in our example, we wanted to eliminate A, B, C. So we give it in a specific order. So we want to eliminate the first A, then B, and then C. And then it run this loop that takes a variable. It makes the products of all the factors that are, of all the matrices that are involved in the variable, and it sum out the variable that we wanted to eliminate. So in the case of the elimination of A, B, C, morally it gives this expression, which is a factorized version of the previous one. So here we are, okay, this is not, oh la la. Sorry. Okay, so here we have we have factorized the sum over A with the three matrices that are involved in A. We put this factor in memory, and then we compute the sum over B. We put it in memory, and then we compute the sum over C. So we get the original vector giving the joint distribution of D of A. Of D and E. And what we have gained now is that you can check that by using this trick of memoization of the intermediate factors in the memory, we can have a computation which is about 2 to the power of 3 operations. So we can gain a bit. Of course, not all orders are efficient in the same way. So there are some that are as inefficient as the naive ways. As for example, if you take a CBA, you will get 2 to the power of 5 basic operation. Okay. Great. What is happening? Okay. Okay. So what are the questions that we wanted to study in this very classical algorithm? We wanted to understand a bit better the nature of the factors that are appearing in the algorithm. So at the beginning, the factors are just stochastic matrices, but as the algorithm is run, the intermediate factors appearing are a bit more complex than just stochastic matrices. They cannot be precisely defined as stochastic matrices. And usually in the literature, they are just described as vectors or matrices of real numbers, while they have a bit of structure in it. And we would like to unlight it. And the second question that we wanted to express is to try to describe this algorithm as a kind of a rewriting over some syntax that describe this factorization structure. So this idea of having a Bayesian network and some nodes that are put together in order to factorize the algebraic expression describing the joint distribution that we want to compute. And in order to answer to these two questions, we use two tools, so lambda calculus and linear typing. So let us give a bit some hints on it. So first of all, we can remark that the Bayesian network in the example, together with the question of computing the joint distribution of D of A, can be described by this term here. So here, okay, it is a let term, but it can be just a syntactic sugar for a lambda term, if you wish. And so here we are saying that actually this let constructor corresponded to the sample constructor used in the previous talk. So it's better to call it a sample. So we are sampling a value from P of A, from the variable A, and then we take this the sample value, we give it to P of B, P of C, we sample a value of B, a sample of C, and so on and so forth. And at the end of this stack of samples, we return the two variables that we wanted to observe. Okay, this term here, if you interpret it in some categorical semantics, in some denotational model, like relational semantics or probabilistic Corner spaces, what you get is exactly the algebraic expression that I give you at the beginning of the talk, the naive one that consists in making the multiplication of the 5 stochastic matrices PA, PB, PC, PD, PE, and then summing out the 3 variables, which is inefficient. The point is that a very similar syntax can express the factorization of this basic algebraic expression. So if you consider the one that improved given by the elimination of first A, then B, then C, well, it can be expressed by these other. So if you look at a bit in the detail, you can see that the first factor, the one that sum out A, corresponds to this sub-expression. So the idea is that the factorization expression correspond to the nesting of the let expression in the syntax of lambda calculus. And eliminating a variable correspond to making a variable local. So here we have this sub-expression here of the term is describing the pink factor here. And you see that the variable a here, xa, is actually local to this sub-expression and does not appear outside. It cannot be used outside. And so on and so forth. This sub-expression here, violet, correspond to the second factor here. And you see that the variable xb is local to the sub-expression. So this is a general, this is a slogan, but it can be applied to any run, any factorization given by the variable elimination algorithm. We can apply it, but in order to do that, we have to introduce high-order variables. So not just ground variable suffixes. If we wanted to represent in that way the factorization given by the variable elimination algorithm. For example, here we have a bit more involved example. Here we have a Bayesian network. And if we are interested to describe the factor obtained by eliminating the variable P1 here, so we have to describe in some sense a matrix that takes P1, P2, P5, P3 and sum out the variable on 1. We will get the problem of this representation is that here we have some output. So the output of P3 and the output of P5 and the output of P2. But the problem is that the output of P5 depend from an input, P4, that actually is depending from another output of the same factor. So we have a kind of cyclic dependence. And in order to represent it in our syntax of let terms, we need to introduce a variable f, which is actually a function, so a functional variable, which describes the possibility of computing P5 once we know the variable that still we do not know, which is x4, which depends from the other variable that is given by this factor that is x3. So this expression here, which is a perfectly well-defined expression in lambda calculus, if you interpret it in a denotational semantics, give rise to exactly the same algebraic expression that you have by applying the variable elimination algorithm and eliminating the variable P1 on that Bayesian network. So in general, here you have the syntax of the terms that we need in order to represent any factorization. So we have tuples of ground variables. So we have let expressions, and then so that is local definitions of tuples given by some expression. The expression can be either a stochastic matrices applied to a tuple of ground variables, or an application of a functional variables to a tuple of ground variables, first-order functions, tuples of expressions, and again, a local definition of an expression in an expression. What you can prove is that if you have any factorization on the Bayesian network, well, it can be represented by a closed term in this grammar. And if you take a closed term in this grammar, you can associate it a factorization in a Bayesian network. So this is the first result, but this is not enough for us. We want not just to represent the factorization as a let expression. We want also to describe the run of the variable elimination algorithm as a kind of letter rewriting. And so the question are, what are the rules that we need to introduce in order to go from a basic let expression like that one, describing the naive computation of the joint distribution, to an expression like this one, describing a run of the variable elimination algorithm. And actually, our surprise was that the rules that we need are just 4, and very simple ones. The standard one are just a let floating rewriting that is quite well known in the community of compilation of functional programming. So here you have the commutation of two lets that does not depend each other. So it's quite a simple one. Here we have the commutation, the possibility of commuting a let that depends from some variables defined before by introducing the this functional dependence here. And here we have the possibility of putting together two let definitions, so to making factors being increasing factors. And here we have the rule eliminating a variable that is not used in the in expression. So this is the one that is implementing the elimination of the variables one. This is used just locally in M and not in Q. So these four rules are enough in order to rewrite any representation of a Bayesian graph into a representation of any factorization of its algebraic expression. And this is given by this theorem. So you take a factorization of a Bayesian network, you applied the variable elimination in order to get a further factorization that eliminates the variable we are focusing on. And you can prove that if you take a let term that represents this factorization, by using these four reduction rules, you get a let term representing the factorization given by the variable elimination algorithm. And this theorem is constructive in the sense that we give a reduction strategy that produces from L this L prime. Okay, great. So a benefit of this work, what we learn from it, for my personal opinion, is the presence of types. So now these terms are completely well typed, and they are well typed by this system here, which is a linear system. Okay, I don't want to enter too much in the details. We are using linear functions because what we duplicate in a term is not stochastic matrices, but are sample values of stochastic matrices. So for that reason, the duplication, so for that reason, these let expression can be defined as linear functions. But the most important thing is that you can, by using standard isomorphism in linear logic, you can rewrite the type that we use to type all the terms we are using in order to represent this factorization by this grammar. So we can this typing system can be reduced to this one, and this one is saying us that the factors that are produced by the variable elimination algorithm are either the tensor unit that is just a value, or are finite coproducts of factors, or are finite products of factors. Now, if you take just the tensor unit that represents just a value, something that is not probabilistic, if you take the finite coproducts of a value, you get what corresponds semantically to the probabilistic distribution, finite probabilistic distribution. If you take finite products of finite coproducts, that corresponds to stochastic matrices. 1 minute, and then you start, and until here we have something that is well known. Stochastic matrices are well known, but then what you get by running the variable elimination algorithm, you can have probabilistic distribution of stochastic matrices of stochastic matrices, and so on and so forth. So the original question we started with was what is the nature of the factor produced by the variable elimination algorithm, and our answer is in this hierarchy. It's a kind of stochastic matrices of stochastic matrices of stochastic matrices, and this way of representing the algorithm give a precise type to any of such factors. And I can stop here. So thank you.
Awesome. Thank you, Mikhail. Any questions in the audience here? Any questions in Paris?
don't think so. Okay, so then if you have more questions, you can go on Slack.
Yeah. Any follow-up questions? Yes, please. On Slack would be great. The URL for Slack is bit.ly/LAFI'23-Slack. There's also one in the email for from one of them from us. Okay, great. So we'll move on to the next talk then. Thank you very much.
Thank you.
Next up, we're going to have Gordon Plotkin.
Good. Is that working?
I think we're making headway.
Can you hear me?
We can hear you. Yes. Can you hear us?
I could always hear you. Yes.
Good.
I'll try and get my slides up then.
But yeah, looks like you're almost here. Yeah.
Good.
Oh no. Can you hear us in Paris, by the way?
Okay. So
Give us one moment. It looks like we're not live.
yeah. Okay. Okay. Sure.
Gordon, if you're there, could you try to share your slides for us?
Oh, I have shared my slides. I put them on the screen. Can you see them?
No, we can't.
Oh, so hang on.
Yeah, they were there for a moment. They'll come back.
What happens now? Now can you see them?
No.
I'm not. What do I have to do? Because I thought my screen was sharing. Is my screen not sharing?
Not at the moment.
What am I supposed to do to make it share? Present to audience. Let's try that. See if
Yeah,
that helps.
give that a whirl.
Share screen. Ah, that should do it. Okay.
We still don't.
How about that? You don't?
No.
Oh, I think I have to click on this thing. Ah, okay, I remember now. Let's see. I think that's getting there. Sorry.
No problem. Hey, no.
Is that better? Is anything happening?
I think progress is being made.
That's okay. Well, how about it? Can you see some slides now?
Yes. Yes.
Good. Well, let's go full screen then. It's getting exciting for me anyway.
No, this is great. Perfect. Okay. Let's
Okay.
see. How can they see us? One moment. Let's make sure they have us in Paris here before we go.
Okay.
All right. We're all ready to start. Thanks everyone for your patience. It's great that we can do these remote. You know, I really appreciate everyone being patient with us while we make this work. Okay. So Gordon, please take it away whenever you're ready.
Okay. Well, thank you very much. So this is joint work, as you can see, by Adam and myself, and the title tells it all. So contextual source code transformations, the idea is that you transform two contexts, and you want to do that because you want to do reverse differentiation. So if you've got two programs, P and Q, and they give you context C and D, and you want to go backwards, you can substitute C and D or D and C, which according to how you want to go. I already talked about this in Paris in June, and since then I wanted to figure out how to extend it to a more expressive language, in particular adding sum types. And sum types are a lot of fun, because the sum types are basically simple manifolds. So you can think of sigma plus tau, it's a manifold, a disjoint manifold, and you have more than one tangent space. At sigma, there'll be some tangent space, and at tau, there'll be another tangent space. So your tangent spaces are dependent, so you need dependent types. This idea has been kind of around for a while, but Nunes and Wacker were the first people to really make something of it. So let's go to some details, and obviously what I just said will be repeated. So the idea is we want to look at three things: reverse differentiation, forward R there, forward differentiation at the top F, and transposition. And reverse differentiation is transposition after forward differentiation. That diagram commutes, and by commuting I mean it really commutes. If you take the source code in the source language S and you do forward differentiation to the target language T, and then you do transposition, you get exactly the same code. So in terms of efficiency, and I care about efficiency here, you get just as efficient code for reverse differentiation, whichever way you go through the diagram. For efficiency, you want to work on anormal forms. So that's the anormal forms of the source language. You translate to the anormal forms of the target language with forward differentiation, but reverse differentiation and transposition, which has to go backwards, has to translate to the context. So I think I've probably said everything in this slide. Oh yes, so but in order to do reverse transposition, you need to know where the linear parts are. So T is a mixed linear nonlinear language. So I guess that's all about that. So on the next slide, something about advantages. Because we do a reversal of computation at the meta level by using context, we don't need to do it at the object level, the programs. So everything here is first order, unlike other pieces of work which use higher types or control flow operators in the target language. We don't need any of that. Everything's first order. And they're all defined by simple structural induction. FT, as we'll see, it's a more or less standard forward differentiation program. The only thing different is it keeps track of the linearity as it does its job. And I've already said the last part, and I've already said the second last part, so that's good. In terms of efficiency, I won't go into any details in the talk, but the headlines are that, excuse me, the forward differentiation is as efficient as one would expect. It's linear. The other differentiation, the other programs are also linear as long as you ignore sum types, and sum types give you a problem. So in any case, they're all space efficient. And if you happen to write a program encoding a DAG of operations, then you're a functional version of the usual backprop algorithm. So the only kind of slight fly in the ointment is the sum types, where you have a problem because computation goes apart and do different branches and it has to be brought back together again, and that causes you some issue. We'll come to that later a little bit. So this is a little very brief primer in context, which I guess everyone knows pretty well. So these are particular contexts, which I call environment contexts. So they're either a whole, or you let X be T in some other context. So these a few little examples. So C is let X be 2 and then whatever. Y is let Y be 3 plus X and then whatever. So if you put D into C, you get let X equal 2 and let Y equals 3 plus X. And if you stick X times Y in that, you get something which evaluates to 10. If you do it the other way around, you get Y becomes 3 plus X, X becomes 2. And if you stick X times Y in that, you don't get a number, you get something which is 2 times 3 plus X. So that's a kind of illustration of how things go forwards and backwards, depending which way around you put the context. So let's, this a little bit more in context. So if we wanted to, it's just interesting to look at how you type context. So we take this little context, let Y be 3 plus X in whatever. Well, it's typed in an environment where X is a natural number, and the context binds y to a natural number. So write x colon that turnstile d, and then I put the binding in square brackets, as it were, in the hole, that y is a natural number. And there's a couple of obvious rules. So for example, well, these are both rules, all the rules. So if you want to type x becomes t and c, you type t, and then knowing that x is a type sigma, now you type c as gamma prime, then the whole thing is typed x of type sigma gamma prime. But notice I've got these square brackets after the x type sigma, and that's because the context might rebind x to some other type, so you have to be able to overwrite. So that's what that does. It's interesting to see how context and terms fit together from a typing point of view. So if a context C binds gamma prime, and you know this is all relative to some other gamma, and you know that gamma prime makes T have type sigma, then that should be a C at the bottom, then C with T is of type sigma. So you could rewrite that as saying that if C has the following type, if you give it something of type sigma, knowing that its arguments are of type gamma prime, then you get out something of type sigma. So you could see it as a continuation transformer. So we are using continuations after all, but at the meta level. And I won't go through the last bit there. Okay. So I want to illustrate how we do reverse differentiation. Well, this is without sum types. So let's suppose, well, this is all for T's normal form. So what we want to do, so suppose T's of type sigma, we want to reverse differentiate it. Well, we're going to feed it some gradient, a y twiddle of type sigma, because that'll be the tangent space of sigma if we don't have any sum types. And we want to output a context that binds all the input variables, the gradients of linear variables. So that's gamma twiddle. So the idea is if gamma is x1 sigma 1 and so forth, and gamma twiddle is x1 twiddle sigma 1 and so forth. But that's not quite accurate, because here we're thinking of everything in the kind of nonlinear world, and now we'll be in a mixed linear nonlinear world, and so the gammas are nonlinear, but the y's and the gamma, the twiddly things, are linear, and so we do use the usual trick of a kind of double context separated by a vertical bar, so a nonlinear on the left, the gamma, and the linear on the right. So given now linear y will bind linear gammas. So you can see in the right-hand side, there's a kind of empty, because we're not thinking about binding any nonlinear variables, only the linear variables. And maybe it's a good point to say that the linear context will be a Cartesian, not multiplicative, because we don't need anything multiplicative here. So keep that in mind, otherwise things may look odd. Okay. So how are we going to use the context? As I already said, if we're going to do E then T, and E gives you some context C and D some context D, T some context D, then we'll just swap them. That's the kind of rough idea, but to get a little bit more precise, to get precise actually, here's the actual transformation. You might think I was going to give you the reverse source code transformation, but there's a bit of a twist. So let's call some other transformation, which I'm going to call I for intermediate. And so what the intermediate transformation does is, well, first of all, it calculates the primal. It says X becomes E. We're in A normal form, so E is going to be a typical elementary or atomic term. Then we're going to expect to get to bind the gradient associated to X. But as usual in these kinds of things, we're going to have to add up many contributions. So we start off with it set to 0. And then we do the context for T. And since that's got X in it, it'll bind X. So it'll bind X twiddle is what it'll do. And E needs the X twiddle, so we carry on and do E. The only reason to have an I and not an R is that we need to just see, if you see this I, it does local initialization of X, but we've got also a global initialization to do for any free variables of the whole program. And so R just does a global initialization, and it's at the bottom there of the screen. It initializes the X's in the gamma to 0. Okay, so now getting into a little bit more detail. Now I somehow hope that I've explained the main ideas well enough, if far too quickly. So here's the source language. The source language is almost pretty well entirely what you'd expect, maybe with one slight twist. So there's basic types, product types. I write them with brackets rather than times for some reason. and some types, sigma 1 plus sigma 2. And the terms are variables, constants, function applications, something odd, a local let x be t and u. We've already had for tuples and projections, components, and in left, in right, and cases. So the only thing to say is that these p's, so I said at the bottom, I'll call them decider terms. They seem like nice things to put in. So the decider term has a sum type p, b plus b prime. I could just have had Booleans, then they would have been of some type 1 plus 1. Does seem more general and fairly harmless. I won't say much about it in what follows. Okay. Target language is a lot more fun. It's going to have dependent types like we saw before in order to accommodate the variation in the tangent space. And it's going to have an odd elimination construct called a bunch construct, which actually was introduced by Nunes and Vacar and is essential to get the typing right. Okay, so the types are B or tuples or this cases thing either. So depending what component you're in according to T, so cases of T, you're either going to be, so T is either going to be in sigma, and then you're going to have some type alpha, which can be further dependent, might be some further sums in there somewhere, or Y, or it can be type tau, and then it'll be beta. So if you look in the example type there a bit further down the slide, if T is of type real plus a pair of reals, then its tangent space at T is cases T of, well, if it's actually in real, then tangent space is real. And if it's actually in a pair of reals, then tangent space is the pair of reals. Product, yeah, well, the space of pairs of reals. And we don't really need the x's and y's because there's no further type with sums in there. Okay, so that's fine. So we have variables, and there are different variables now, right? V, thinking of vectors, with zeros and sums. And where we had a function before, we now are going to be either forward or reverse differentiating with respect to a single variable. So we have a single, linear argument there in these functions. So f of non-linear is t1 through tn and a single linear. All this would it would get worse in other circumstances, but here it's nice and simple. Won't bother about the p's, as well as the non-linear one let we have before. We now have a linear let. So let V be alpha in A and then carry on with A1. An interesting thing here is this T cases thing. So the idea is to have in your head this T and A. So T, if you think in terms of manifolds, T is a point in a manifold. And at that manifold point, there's going to be a tangent space, and A is a vector in that tangent space there. That's a general idea. In terms of typing, a formal typing, T will be of type sigma, and A will be of, T will be of type sigma plus tau, and A will be of type cases T of X colon sigma something, Y colon tau something else. That's how that's going to work. I think that's everything in that slide. Here's how to type linear language. And then the thing that I've spent most time on since Paris in these several months is getting this to actually work. And you might expect, and you would expect, that you'd have, okay, you've got dependent types, so you're going to have type equality. And we're certainly going to have these new linear contexts. So they're going to need a gamma and a delta and bind some other gamma and delta. But we also need this subscript C. And the reason is best explained. These are the contexts as before. Why do we need these contexts? The idea is as you go down in the term, you're going to build up context by the nonlinear lets, which is fine. But it turns out you need to use the information that gives you to do the typing. So if you look at the middle rule there, for example, not for example, this is a critical one, then we want to type let x be t in A. Okay, fine. So to do that, we assume that x is of type sigma, delta isn't affected, and we say that we type A as being of type alpha. But the point is, when we come back downstairs from there, alpha had better not have x in it, but there's nothing stopping in the above part alpha having x in it. So we need some way to get rid of x. So how can we get rid of x? Well, we happen to know that in that context, x is going to be equal to t, and t will be typed higher up. And even if there's some x higher up, it's a different x. So we could substitute t for x in the typing there of alpha, which in case it does have x in it, and that will produce a different alpha, which you can then put down to the bottom. So we have to use that information somewhere, and this is where the information comes from, and it's used in the typing rule for a particular typing rule for equality. So type equality relative to a C, and that rule is there. Though to see how it works, you'd have to have the rules for equality in front of you, which we won't have. So that's fine. Let's see. So for anormal forms, so I've just lost track of my timer here. That's better. Very little time as always. Anormal forms, obviously elementary terms and assignment. The target language, the anormal forms are just the things that would correspond to that. I think this is ignoring sums. So type translation, without types, the type translation from these are the idea of the type translation is given a type, is translate is a type is a tangent space, a dependent tangent space. So there's nothing to happening without some types. With some types, if you look at the bottom one there, the question is, what's the tangent space of sigma plus tau at the term t? Well, it depends what t is. So it's written by cases, and if it's in x, then it's the tangent space of x, sigma at x. Otherwise, it's the tangent space of tau at x, and you have to fill a bit with products. Okay, forward differentiation is exactly the same as before, but you have to take the dependency into account. So for example, if t is of type sigma, then f of t is of type, it's going to be the tangent space of sigma at t. So it's sigma twiddle sub t. Good. Forward differentiation. So I always write too much. So what interesting things to look at in this slide? Well, nothing too important. Given the time that's left, I can come back to the slide if people want. Reverse differentiation is, well, again, it's just exactly what we had before, except you have to make allowance for the tangent spaces. So for example, if t is of type sigma, then the gradient you'd want had better be in the tangent space of t at sigma twiddle. So the gradient is the sigma twiddles at t. Otherwise, it's the same. The gammas also are dependent on the gamma twiddles. For reverse differentiation, I would maybe point to the last line, and that's exactly what we had earlier when we were just talking more generally about motivation. It's exactly the same thing. I mean, actually modified by the dependencies. There's not really much to say about anything else really that isn't standard. So for example, if you want to reverse differentiate a function application f applied to some primal variables x's, you just do all the partial derivatives. For example, for x1, you update x1 by the partial derivative of f at y. This particular f is linear, so it doesn't need any of the primals. So there's nothing very much going on really. Transposition is, well, it's just a version of that. It's exactly the same, roughly speaking, exactly the same as the reverse, except you rub out all the twiddles. Instead of writing x twiddle, you write v for a variable. And so that's how that works. So for example, we want for the transposition of A, if it's bound, if it's typed in type sigma and its type is of type alpha, then as it were, going backwards, you'll come in with a V of type alpha and you'll bind the delta. So you just go exactly the right way around. There's no twiddles or anything because they're all linear now. Okay, and the translation, let's see, I wonder if there's some interesting things to say. So if you look at the second last line, then when you do a transposition on an assignment, a let expression, you don't need to do anything with the primals any longer, because you're only interested in the linear part, and that's nothing to do with the nonlinear, the primal part. So you just transpose the A. On the other hand, if you're trying to transpose a linear let, then you do have work to do in both the M that you're letting and the body. So you do, and it's exactly the same as before, but it's linear. And I guess I don't want to say anything too much, given the time I've got left, about the rest. So this is introducing cases. You want to do forward differentiation. And it turns out forward differentiation is really easy as long as you use this bunch thing. So the forward derivative of a case is So we want to look at y. So we're examining some y, but we want to know not only what the y is, but what the tangent is as well at that for a particular y. And then there'll be two different cases, and we can just use each of these separately. An interesting thing there is, in some sense, you might be surprised there's nothing about cases in the target language. And this here, the top line there shows you what's going on. The f of in left of x is just x twiddles, because the tangent space of in left of x, the tangent space, so x is going to be a sum type. Excuse me, in left of x is going to be of some type. But in left, say sigma plus tau. But in left of x will be in the sigma part, which is exactly where x is. So the tangent space of in left of x at in left of x will just be the same as the tangent space of x. So that's why you can get away with that. A reverse differentiation. Oh, that's good. Coming back down with 12 seconds left. I just want to put, it's a very nasty giant thing, but I want to just give a slight feeling for what's going on. So when you reverse differentiate our cases, as you'll see, sorry. When you reverse differentiate cases, you have to reverse differentiate each of the branches, or you may have to. Each of these branches will give you a context which binds the variables in there, but to pass it out, and we have to pass that information out. So we evaluate some giant tuple, and then outside that, we look at all these elements of the tuple, and that just takes you more time, and that's where the lack of efficiency is. But it's only, well, it depends what your program's like, but it's to do with the number of variables that the cases do and the depth of the cases. So it's not too good and it's not too bad, and it's somehow life with cases is always hard. Okay, so one would like to do a lot more, but probably it's a good time for any questions. Thank you.
Awesome. Thank you so much, Gordon. We're a little bit behind, so if there's any questions for Gordon, please feel free to send him an email. We can chat on Slack as well. So next up, we have Tim, going to be remote online. And we're transitioning into the lightning talks portion of the workshop now, so it'll be 5 minutes long. So again, I'll remind you, please stick to 5 minutes.
Hi, I don't seem to be able to present my screen. I think someone else is still sharing it.
Yeah, we hear you. We're getting you set up here still.
Cool, thank you.
And that's Tim. Hey, Tim, could you try to share your screen for us, please?
Yeah, I have a button, but it says only one person can share screen at a given time, and it's like grayed out, and I can't click it.
Got it. That's helpful. Thank you. Maybe we can ask him. Now he can share. Great. Tim, could you try again for us, please?
Yes, trying.
Ta-da!
All right, can you see my screen?
We can. All right.
Perfect.
Thanks for your patience, everyone. I think we are ready to go.
Great.
One sec. Let's make sure.
Sure.
All right. I think we're just going to get started. Okay. With that, I'll give it to Tim. Take it away.
Great. Thank you very much. So yeah, my name is Tim, and I'll be talking about some interesting behavior of posterior distributions in probabilistic programs, and this is joint work with Luke Ong and Tom Wainford. So in general, we can view probabilistic programs as defining unnormalized density functions, which will denote gamma from here on. And then the task of inference is usually to find a representation of the normalized density function, which will denote as pi of x, usually from here on. And so-called universal probabilistic programming languages allow for language features such as branching on the outcomes of sample statements, which then leads to programs with stochastic support. And previous work has showed that in these models with stochastic support, the posterior can be decomposed into so-called straight line programs, which can be viewed as the control flow path in the program. And this decomposition allows us to write the posterior in probabilistic programs as a weighted sum of the posteriors in the individual SLPs. And the weights, WK, depend on the normalization constants, ZK, in each individual SLPs. Now, our insight for this work is that we can effectively view this decomposition as a Bayesian model average over SLPs. So each SLP is kind of like one of the candidate models in the Bayesian model averaging. And this provides us with an interesting angle to reason about the behavior of posterior distributions. And one crucial assumption that Bayesian model averaging makes is that one of the models in the average is the true data generating process. So in the context of probabilistic programming, that means that we're implicitly assuming that the data was generated from exactly one of the SLPs in our program. And recent work in statistics has shown that if this assumption doesn't apply, then we can get posterior model weights, which can be wildly overconfident. And let's look at an example of what I mean in particular. So here on the left, we have a Pyro program with two SLPs, meaning two control flow paths. And in each SLP, we're trying to estimate the mean of a Gaussian. And the two SLPs differ in that we make different assumptions on what the standard deviation of that Gaussian is. And furthermore, we assume that the true data generating process is a standard normal. And now we run experiments by generating multiple possible data sets. And in each data set, we compute the posterior weight for the first SLP in the program. And then we look at the distribution of that first weight. And that's what's plotted at the bottom right in figure 2. And what we can see is that the posterior SLP weights collapse on either 0 or 1. And that's really undesirable behavior because it means that our posterior weights, or our inferences in general, are not very robust to minor changes in the data. And note here that this is a property of the analytic posterior, and the stochasticity here comes from generating multiple data sets and looking at the behavior over multiple data sets. And while this is a relatively small scale toy example, this behavior has been observed in practice in models in economics and phylogenetics. And also there's been theoretical analysis underpinning these results and showing that this behavior doesn't go away if you just use more data. So this really motivates the need for alternative ways to compute our SLP weights in our probabilistic program posteriors if we don't want to have this non-robustness. And one potential solution we're currently looking at is stacking. In stacking, we try to optimize the SLP weights to improve the predictive performance on unseen data. And here, the stacking objective that we're trying to optimize is shown on the left, where we're trying to maximize the log posterior predictive density. And rho in our objective gives the predictive density of our input program, where rho itself is a weighted average of the posterior predictive densities of the individual SLPs. And note that our expectation is under the true data generating process. And of course, in practice, we can't observe that we don't have access to the true data generating process. And instead, we approximate this expectation using a held out validation set, which is a common practice in machine learning. And like initial results seem to suggest that stacking leads to more robust weights and also to better predictive performance. And this is very much still ongoing work and work in progress. And so I'll be very happy to hear people's thoughts and questions either on Slack, or you can also contact me on via email. Yeah. Thank you very much.
Awesome. Thank you so much, Tim. Next up, we have Marie.
Can you?
Yes, we can hear you.
Me? Okay, so let's go. So what I'm going to about this very much.
Sorry, hold on one minute, Marie. We can't see your slides.
Okay.
Give us 1 second.
Okay.
Yeah, Murray, could you try to reshare, or if you aren't, could you try sharing?
So I was sharing, but I'll reshare.
Yeah, we can see your camera, but we can't see your screen.
So are you seeing my screen now? I'm supposed to be shared.
That's weird. Huh. Okay.
I'm sharing on my side.
Yeah, we're just getting a black screen when you're sharing your slides.
Okay.
Yeah, is it possible for you to
no.
try sharing without full screen? Maybe you could just show the screen, like share part of the window or something?
Sure, I'll try one time, and otherwise maybe.
Yeah, try stopping your camera as well. The connection might not be good enough.
Okay, thank you. So I'll stop my camera, and can you see my screen or not?
It's loading. Yeah, unfortunately, we're not getting your screen. So, okay.
Maybe you should go to the next speaker, and I'll try to sort it out.
Yeah, but you should upload your slides onto Slack, and we will talk to you.
Yeah, I'll do that. Thanks.
All right. Yes, no problem. Sorry about that. All right. Now we are transitioning into the part of the workshop that is here physically. So in Boston, I mean. So next up, we have Dominic Wagner, and I have your slides.
Oops. Let's do full screen. That's better. Yeah. Is everything set up? Okay, yeah, I think I can start, can't I? Okay, great. Yeah, so I'm Dominic, and today I'm going to talk a bit about the reparameterization gradient for non-differentiable but continuous models. So as you are probably well aware, variational inference is a very successful approach to Bayesian inference, and the basic idea is to frame posterior inference as a deterministic optimization problem. So in slightly more detail, so we posit a family of, or a variational family of simpler guide distributions, and then the aim is to find the guide which is closest to the true posterior, where closest is formalized as the KL divergence. So abstractly speaking, we have an optimization problem of an expectation of a function which depends on some parameters which we aim to optimize. And the standard approach in practice is then to use stochastic gradient descent. And the key ingredient, as the name suggests, is the estimation of the gradient of the expectation above. And there are essentially two kind of classes of approaches. One is this, what is called the score estimator, which is very widely applicable, but suffers from typically a high variance, which means that convergence is either slow or very unstable. And then there's the reparameterization estimator, which behaves much better in practice, but which may be biased, as Lee et al. Have shown at NeurIPS 2018. And the problem is that the function is expressed in a programming language and hence may not be differentiable or continuous. Now let's consider an example which is also containing some branching, where we model some temperature regulation system. So initially, we start with a temperature of about 20 degrees, and without intervention, just the temperature changes or fluctuates randomly around the current temperature. And if it drops below a threshold of 19 degrees, then we kind of increase or start the heating with power proportional to the deviation from our threshold of 19 degrees. And then we kind of, after one time step, we observe 21 degrees, and based on the kind of how we change the temperature. And now we may be interested in how the initial temperature has actually been based on the observation. And if we now draw the density, then we see that this is a non-differentiable model. So we may think that it may perhaps be biased if we just do the renormalization gradient estimator. So in this work, I've been asking the question whether the renormalization gradient estimator is biased for continuous but possibly non-differentiable programs. As we've seen, this was continuous but non-differentiable. And the answer to this is no. So we can actually safely apply it for continuous but non-differentiable programs. So to formalize everything in this work, we consider a kind of standard toy simply type lambda calculus setting with primitive operations of a certain class and sample observe statement. And of course, there's also branching, which we may restrict in some settings to ensure continuity. And there's also a smoothed branching construct, which extends the explosivity. And so as a first step, we introduce also a denotational weight semantics, which is essentially a denotational version of the standard weight or density semantics. Then because we are interested in continuity, we have to go beyond measurability. So we can't just use the QUBS type model, but we have to capture more properties like the piecewise definition, sort of a PAP style thing, and continuity. And then a slight complication is that we want to interpret these higher or these smooth conditionals, which we also want to interpret at higher order. And the approach we take is to generalize the construction of Rayleigh spaces in a certain way, something which we've also been doing in a paper which will appear at ESOP. And based on this denotation semantics, then we can show that the estimator, the renormalization gradient estimator, is unbiased for terms without conditionals. And as a example, we can, for example, rephrase the initial running example by using a value function. Now, next, because we may actually be interested in having proper conditionals and not just non-differentiable primitives, we may be interested in establishing continuity for terms with branching. And so the naive check is unfortunately intractable, sort of just applying the definition of continuity, but we can use a trick inside, namely that if we have analytic primitives in both branches and we have kind of a comparison in the guard, like x minus 1 less than equal 0, then this is continuous by definition if and only if on the boundary the difference is constantly 0. And now we exploit a property of analytic functions, which is that they are either constantly 0 or 0 on a negligible set of measure 0. Therefore, we can just sample from the boundary and check on a sample point on the boundary whether they agree. And this check is now correct with probability 1. But of course, we need to be able to sample on the boundary, and this is not always efficiently possible. Therefore, we restrict our attention to affine terms because then we can do it efficiently. Furthermore, this restriction to affine terms also has the advantage that we can check the consistency efficiently by a kind of linear arithmetic solver, which is then important in other situations. Okay, so yeah, if you are interested in hearing more about this, then there's a paper in which, a poster, in which this is shown in more detail, so that the renormalization gradient estimator is unbiased for continuous but was possibly non-differentiable programs. And the main benefit for practice is that this provides the foundation for fast yet correct inference for probabilistic programming. Okay. Thank you for your attention.
Thank you, Dominic. Next up, we have Oscar.
Okay, thank you. So my name is Oskar, and I will talk about our work in progress on partial evaluation of forward mode automatic differentiation. And this is work between myself, Victor Palmqvist, and David Broman. So forward mode AD is asymptotically efficient, but it requires a non-standard representation of the real numbers in the form of, for example, pairs encoding dual numbers. And this leads to a constant runtime overhead, as we cannot directly compile the elementary functions to cheap floating point operations. On the other hand, symbolic differentiation does not suffer from such runtime overhead, and it also allows us to do expression simplification at compile time. However, it is not as expressive as AD in the sense that we cannot always symbolically differentiate all expressions in more expressive languages, including general recursion and higher order functions, at least not at compile time. So the research challenge that we're addressing is how we can combine the strength of ST and AD while mitigating their weaknesses. So the key idea is to use partial evaluation of AD to combine the expressiveness of AD with the efficiency of ST. And this is an idea that has been proposed before in the literature. However, in contrast to previous work, we define a whole program transformation where we explicitly handle lifting and differentiation of free variables. From a high point of view, we can view our transformation as a pipeline where we have some input program that may contain some DER constructs. And then we do a partial lifting of this source code. So we lift the parts that are affected by differentiation, possibly duplicate some code to avoid having to operate over dual numbers. Then we employ the standard forward mode AD transformation to generate code for computing derivatives. And then finally, we partially evaluate this generated code in order to sort of reduce the need to operate over these dual numbers. The key challenges when considering whole program transformation is that derivatives may contain free variables, in this case f, and we have to somehow lift these. We cannot simply substitute f for its definition before lifting, as this would generally lead to a code explosion. It may also be the case that f is used here both inside and outside a differentiated expression, and since and we don't really want to call f a lifted version of f outside of the differentiated expression, as it is associated with a higher runtime cost of operating over dual numbers compared to floating point numbers. So the key idea is to keep both a normal and a lifted version of f, which we call f hat. For left-bound expression, it's easy to add an additional version of f called f hat, but it's more challenging for higher order function, as the definition of f hat will depend on the place of application of this expression. Here instead, we try to add an additional parameter f hat to this expression, and then we also have to update relevant parts, relevant places where we do the application of this expression. And the way we keep track of this is via propagation via the type system. There are still some unsolved challenges here with regards to transforming sum types and pairs. It's also the case that when we do the partial evaluation, when we encounter a free variable, sort of the partial evaluation holds, and their code is essentially similar to pure AD code. We can improve on this for scalar functions, for example, by instead of lifting f to f hat, a free variable f hat directly, we can lift it according to this relation, where we essentially lift it with using itself and the free variable f prime, which denotes its derivative. And we can then construct the definition for this derivative f prime using the DER construct itself and the definition of f. And then we can generate efficient code for computing it by like recursively employing the transformation on this definition. There's also some standard challenges related to recursion when you do partial evaluation, such as code explosion and termination. And the idea here is to take a pragmatic approach where we sort of use a user-defined max recursion depth and basically unroll the recursion until that depth, and then leave the rest of the computation to the runtime. Okay, so that is it for me. You're welcome to join me at my poster if you have more questions.
Thank you so much, Oscar. Thank you. Next up, we have Christopher Lamb.
Put something.
Yeah.
Okay. Hello. So I'll be presenting for Pedro and I for distribution theoretic semantics for non-differentiable programming. Pedro already did one presentation today, so I'm doing the other one. But yeah, so the goal of this work is to solve two problems, both of them involving if statements. The first is the following. You can kind of represent the same function in many different ways using if statements in a way that breaks automatic differentiation. So like take this function here. It's effectively exactly the same as this function. It's just the identity function, except for this case at 0. And the problem is what automatic differentiation and like in practice, what it does is it goes down each branch for the conditional. So while the derivative of this is fine, it's just 1 everywhere. The derivative of this one, when you go down each branch, is 0 at 0. So this is unsound because even though these are exactly the same function extensionally, the derivative of each one is different when we run down each branch, and that's bad. So that's unsound behavior. The other problem that we're hoping to solve with our work is that non-differentiability exists. When we try and differentiate a non-differentiable function, we end up with problems like ReLU's non-differentiable. There's like the Heaviside function. Anytime you have conditionals anywhere, you will generally break things. You'll generally break differentiability. And so the solution that we propose for this in this work that we hope to resolve these two problems with is distribution theory. And the general idea behind distribution theory is that instead of sampling at a point, you sample a neighborhood around a point. Oh, sorry. Let's just pick this up. So let's say we have this just nice parabola here. And we want to, instead of sampling at this point at 2, what the distribution will do is it'll take this weighted average around this bump and integrate these two functions together. And this bump, it's important that this bump has some nice properties. First is it has to be infinitely differentiable, and second, it has to have compact support. And so if we call this function f and we call this bump phi, then formally what we do is we just integrate them together. And that's how we take the weighted average around this point of this function. And this is how you can evaluate these things. Phi also, it's also important that phi is a pretty simple function, and then you can also change its magnitude, so its height and its radius very easily. These are two constants in the closed form that you can just change. And so we call this formally, if we want to take a function and turn it into a distribution that takes these bump functions, which we'll call test functions, to distributions, we just lift the function f. So what can the function f be? F can be anything that's locally integrable. So it can have a lot of discontinuities. It can be broken up in a bunch of different places. It can be non-differentiable in many places, and you can still lift it to a distribution. And the important part about this is that, before we get to there, this is just another thing that we'll use notationally later. So this is just saying, if b is true, then evaluate f at that point. Otherwise, send it to 0. And so an example of this is just the Heaviside function. If it's less than 0, 0. If it's greater than 0, go 1. And an important part about being able to lift all of these non-differentiable functions into distributions is that distributions are by definition infinitely differentiable. And so this identity up here gives us where this notion of differentiation comes from, in that for smooth functions f, differentiation here, this identity holds through a simple integration by parts argument. And so we can just define distributional differentiation more generally using this idea. So instead of taking the derivative of the distribution, you can instead take the derivative of the test function. And like I said earlier, the test function is always infinitely differentiable, so you can differentiate anything this way. And it will agree with your traditional notion of differentiation. And so if you want a more closed form, this is it. It's kind of ugly, but the general idea is at any point of discontinuity, you stick a Dirac impulse in there and multiply it by the magnitude of the discontinuity. And so we're onto our language now. This is basically just simply typed lambda calculus, except for 3 new types: pred n, which is just the type of predicates for our conditionals that we mentioned earlier. drn, which is just our test functions, our bump functions, and d prime rn, which are our distributions. And like I said, the language is effectively just the simply typed lambda calculus, except with our distribution theoretic primitives. So just lift our conditional, differentiation, distribution application, and our bump function construction. And so there's some basic typing rules. This is just, you're turning a distribution or a function to a distribution. We're taking our conditional, so taking your predicate and a function and turning it into a distribution using construction from earlier. This is differentiation. We can only differentiate, in this language, we can only differentiate distributions for technical reasons involving this semantic model behind this. More details come for a poster. And then this is just how you apply a distribution. You take a distribution, you take a test function, you just mash them together and you get back a real number. So lastly, this is a simple example. This is the Heaviside function. When you differentiate it, this is what the differentiated program looks like in our language. You just, using the third line or the third line of the differentiation slide from earlier, you just add a Dirac impulse there at magnitude 1. And yeah.
Great. Thank you so much, Chris. Next up, we have John Lee.
So what do I do?
I mean, just click this one somewhere.
Okay. Hold this.
Yeah, or just your pocket or whatever.
All right. Okay. Okay. Hello. Yeah, I'm John, and this is New Foundations for Probabilistic Separation Logic. This is joint work with Amal Ahmed and Steve Holdson at Northeastern University. So a lot of our work is motivated by this question, which is we are trying to find out how we can modularly verify probabilistic programs. Probabilistic programs are getting larger as applications are using more and more machine learning, and we would like tools that support the modular verification of these larger and more complex programs. So in the traditional setting, there's separation logic. Separation logic has been super successful for the verification of concurrent imperative programs. And the key thing there is this separating conjunction connective, which says that a separating conjunction of P and Q holds of a heap if you can split the heap into two disjoint parts, which individually satisfy the corresponding conjuncts. And we want something like this for probability that would allow us to kind of chop up a program into probabilistic components. Oh, the animation's a little messed up, sorry. So if you look in the literature, there are papers that try to apply separation logic to the verification of randomized algorithms. And in these papers, star pretty much means the normal thing that it usually means in separation logic. So when you write star, it means something about the disjoint union of heaps, more or less. And that's really good for the traditional notion of modularity that separation logic gives you. But in our setting, when we have probability, there's this new notion of resource, which is randomness. And ideally, we would like star to also allow you to reason modularly about randomness. And so one natural idea is, well, maybe star can mean something about probabilistic independence. And there are, in fact, papers like this. So there are a lot of papers where you write down star, and it means something about probabilistic independence. And in these logics, the semantics is based on distributions on stores. So if you write a proposition, what it means is a set of sort of distributions on random memories. In our work, we take a slightly different tack. So we have this new model of separation logic. And instead of using distributions on stores, we model a proposition by a set of probability spaces. So what does that look like? Well, essentially, if you take the old separation logic picture in the traditional setting, all we do is we replace all the heaps with probability spaces. So all the heaps become probability spaces. And then in the old interpretation of separating conjunction, the disjoint union that's used to split a heap becomes this new bulleting operation, which is an operation for combining probability spaces that we've come up with called the independent combination. That's just what we call it. And this actually leads to a logic with a lot of benefits. So what we've done is we've built a program logic on top of this for reasoning about Markov kernels. And if you look at, for example, the frame rule for that logic, it's completely identical to the standard frame rule. So this is in contrast to prior work. There are no additional side conditions you need about the random variables involved in order to make the frame rule work. Also, because our model is based on these probability spaces, these really super basic objects of probability theory, we can kind of import a lot of results super easily. So this makes it super easy to support continuous variables, makes it easy to validate like equational reasoning principles, and it also let us kind of make this modal approach to conditioning. So we have this modality, and if you stick it in front of propositions, it kind of just means the thing that you think it does. So for example, y star z, that means y and z are independent. If you stick our modality in front of that, then it means y and z are conditionally independent. And it happens with other connectives too, but this is just an example. We use all of this to verify what we consider a challenging weighted sampling algorithm. If you want to see all the details of this, you can check out our poster over there. And if you look at the poster and you want to see even more details, you can check out the paper in the link. So, thank you.
All right. Thank you so much, John. And next up, we have James.
Look all right. Yeah. Hi everyone. So yeah, I'm going to talk about this this work on verified reversible programming for verified lossless compression that I've been doing with Jan Willem over in Amsterdam. So why am I interested in reversible programming? So in my kind of day-to-day work, if you like, I kind of design and implement new lossless compression algorithms. And a lossless compression algorithm actually always contains two functions, an encoder and a decoder. And we require these to be exact inverses to each other. That's where the losslessness comes from. So I've got some Python code that kind of exemplifies the type of code that I might write. So on the left, we've got an encoder, and on the right, we've got a decoder. And I won't kind of go into the details here. What I want you to observe is like the high-level structure and the fact that there's a correspondence between these two functions. So the middle operations correspond to each other, like the top operation of the left-hand function inverts the bottom operation of the right-hand function, et cetera, et cetera. But there's actually a bug here. So I put this in to kind of illustrate the kind of bugs that happen in the programs that I write. I don't know if anyone spotted that, but I think those bugs are quite hard to spot by eye. And to find them, you often have to kind of do this manual bisection process where you pause the encoder in a certain state, pause the decoder in a certain state, and check that everything matches. And you kind of effectively do this like binary search through the programs to find out where things are incorrect, and it's a real pain. So there's a question of like whether we can prevent that kind of bug automatically. And I guess more conceptually, like it feels like it ought to be possible to express both of these functions in one function, which can be both done and undone, i.e. a reversible function. So I've written a tiny language, which is a pure functional language embedded in Agda, which I've called Flipper. This is a kind of high-level overview. I'll start in the bottom right. So this is the type of reversible functions, and it's a record type. So to build a reversible function, you have to write an apply function, which is the sort of do, an unapply function, the undo, and then these two proofs of correctness. So the first proof says that for all A, unapply of apply of A is equal to A. And then the second proof says that apply of unapply of B is equal to B. So they're kind of obvious bijection properties. This type is often called an isomorphism in the functional programming literature. Yeah, and then, so how do you make one of these? Well, you can build one manually yourself if you want to, but that's kind of boring. So what's more interesting is that I've written a sort of little compiler as an Agda macro, which takes an implementation of apply and basically generates the 3 other record elements automatically. And it turns out for this like small grammar, if you kind of express your function in this particular way, then those 3 things are actually pretty straightforward to generate. But this language is general enough for my purposes. So it's a very selfish project. I'm really doing this just for myself. This is general enough to express the lossless compression methods that I want to implement. I've got a tiny sort of trivial example here. So this is a reversible function that swaps the elements of a pair. So maps from a Cartesian product reversibly to this other Cartesian product here. F is that compiler macro being applied to a lambda. And one thing that's quite nice about Flipper is that you can see syntactically what the result of reversal is going to be by rotating the source code. So that's where the name Flipper comes from. And actually, you have to do this 2-stage kind of physical transformation to the source code. So you firstly rotate it, and then you have to upright each symbol. And that includes the constructors. So those commas have to be uprighted. And you have to move the lambda over to the left. So the lambda actually, that's kind of an ugly thing. But anyway, this is the unapply that you get by, so it's global rotation followed by local rotations. Okay, so that's kind of it for the talk. A few things. Oh yeah, still need to finish the compression implementation, but it's all finished. It just needs to be sort of glued together, and I need to set up I/O and stuff. Maybe like make Flipper into a standalone language. So there are some slight limitations due to the way that it's embedded in Agda. In particular, some things which it should be straightforward to prove that they terminate. Agda's termination checker actually doesn't do that. So you have to like shout at the compiler in capitals terminating to sort of say this function does terminate. Yeah, and I'm also on the lookout for other use cases of this reversible language. Anyway, yeah, that's it. Thanks very much for listening. It's all on GitHub here.
All right, that's it for the LAFI talk program. So great to see you all, and so stick around. No, that was not going to be a talk right now. So stick around. There's going to be a poster session afterwards. So everyone who has a poster, make sure you put it up around the wall. We have tape up here in front. There's coffee outside, don't forget. And there's going to be a dinner. It's an informal dinner. We're going to a large kind of food court area with lots of seating. So feel free to meet us there at 6 p.m. It's called Boston Timeout Market. And we'll hope to see you there. Okay.